there is no way of knowing when a given nucleus will decay. You can only try to characterize the overall behavior of a large number of nuclei. For a given sample, while the radioactive decays are going on, the number of parent nuclei will be decreasing. But this decrease is not linear with time. The sample does not lose the same amount of parent nuclei per second. Experimentally, choosing a time interval, the proportion of nuclei left at the end of that time interval compared to the amount of parent nuclei that was there at the beginning of the time interval is a constant. Let us use the variable r as this constant proportion. This statement written as an equation looks like this, where the top expression is the number of parent nuclei at the end of the time interval, and the denominator of the fraction is the number of parent nuclei at the beginning of the time interval. In order for the number of nuclei to be decreasing, r needs to be smaller than 1, and we do not want a negative number of nuclei. Exponential functions are based on this sort of condition. It is useful to use the time interval for a given ratio as a comparison for the time scale of the life of different nuclei. The customary ratio r used for this comparison is 0.5. The time interval associated with this ratio is called the half-life. We will use the symbol h for the half-life, not to be confused with our previous use of h as a height. So, in other words, the half-life is the time it takes for a sample to lose half of its parent nuclei. Half-lives have a wide range of values. For example, uranium-238 has a half-life of about 4.5 giga-years. So uranium samples are radioactive for a long time. In contrast, the half-life of the daughter nucleus of the alpha decay of uranium-238 is only 24 days. Shorter still is the half-life of bismuth-214, where half of it is gone in 16 milliseconds. To make prediction on how much a parent nuclei is left, we can return to our previous equation using the time interval as h and the ratio r as 1/2. This can be written in this fashion. In particular, the number of nuclei left at the half-life is half of the value of the number of parent nuclei at the chosen time origin, labeled n0. Evaluating n at 2 half-lives can be written in this fashion. And using the above result for NH, we can write this. You can keep on going for n at 3 half-lives and use the preceding result for n2H to write this. Hopefully you can see the trend and conclude that the number of nuclei left after a multiple of half-lives can be evaluated using the number of nuclei at the time origin, n0, and the number of half-life since the time origin. This is a graph of the percentage of the original amount of parent nuclei left as a function of time from the equation we have just discussed for n values from 0 to 5. You can see that at time 0, the time origin, the percentage is 100%, which is the same as 1. After 1 half-life, the percentage is 50%. After 2 half-lives, the percentage is down to 25% of the original amount. Going further, the graph would go asymptotically to a percentage of 0. The percentage could have been evaluated from the ratio of the number of nuclei or the ratio of the mass of the nuclei left in the sample. But what if we want to know the amount after a year? And a year is not a multiple of the half-life. Let us look again at the equation for the percentage of the amount of nuclei left compared to the original amount. The product of NH is the time, so T equals NH. And from that, we can write that N equals T over H. Making that change leads to this. We can calculate the percentage at time other than multiple of the half-life by allowing N to be a real number, not just an integer. We can interpolate between the dots that way. Let us do an example. In this example, we start with 145 grams of iodine 131. The half-life of this nucleus is 16 days, and we want to know how much will be left after a week. The amount of radioactive material is given in grams, not in number of nuclei. So we will use the symbol for mass. The givens are the original mass, the half-life, and the final time, which needs to be expressed in the same unit of measurement as the half-life. We then use the equation for the time dependency of the amount of radioactive material. Since we are working with mass, we will modify it to account for that. Substituting the givens leads to this. Using a scientific calculator with the function x to the power of y, we get this numerical answer. This is the final answer. The knowledge of the time dependency of the amount of radioactive material can be used as some kind of long time clock. We will look in particular at the decay of carbon-14. Carbon dating was first proposed by Dr. Willard Libby in 1946. It has just been discovered that this isotope of carbon was created in the upper atmosphere from the interaction of cosmic rays with the nuclei of nitrogen-14 through this nuclear reaction. This isotope of carbon has a half-life of 5,730 years. In comparison, the other isotopes of carbon, carbon-12 and carbon-13, are very stable, to the point that in practice they are said to have infinite half-life, or no half-life at all. These two isotopes make up the majority of the carbon in the atmosphere. One of the assumptions of carbon dating is that the ratio of the amount of carbon-14 to the amount of carbon-12 in the atmosphere is constant, and as you can see, very small. Not only is it constant in the atmosphere, but carbon-14 nuclei find their ways throughout the entire biosphere, so that this ratio is valid for the carbon content of all living organisms, past and present. However, once they die, they get isolated of the cycle of life of eating, breathing, and making waste. They are considered a closed system, which is another assumption. After the death of the tissues, the carbon-14 nuclei decay into nitrogen-14 by beta-negative decay, and the ratio of the amount of carbon-14 to carbon-12 in the once living matter gets progressively smaller. Let us do an example to show how to estimate how long ago a sample of bone would have died. In this example, the mass of the carbon-14 and of the carbon-12 in a bone sample was found experimentally. We are looking for how much time elapsed between the death of the bone and the time at which its mass analysis was done. The givens are the mass of the carbon-14 at the time of the analysis and the mass of the carbon-12 at the time of the analysis. However, since carbon-12 is very stable and the bone is considered to be a closed system, this mass of carbon-12 would be the same as it was at the time of death. Here we have just set the time of death as having happened at the time origin. It was already mentioned that the half-life of carbon-14 is 5,730 years, and the ratio of carbon-14 to carbon-12 in all living things is 1.4 times 10 to the minus 12. This would also be the ratio at the time of death. In order not to drag the numbers in the equations, I will label this ratio as K. Let us start with the time dependency equation for the decay of the carbon-14. And next, use the constant ratio of carbon-14 to carbon-12 to evaluate the mass of carbon-14 at the time of origin. In this equation, the only unknown is T, which is what we are looking for, the time since death. Isolating for T involves the use of the logarithmic function, which is not a subject normally covered in grade 11. You can still solve this equation by trial and error and the use of the x to the power y function on your scientific calculator. Notice that the left-hand side is equal to about 65% after substituting the givens. It means that the time t must be less than the half-life since the sample had not lost 50% of its carbon-14. This reduces somewhat the range of trial values for t that would lead to a percentage of carbon-14 left near 65%. I will, however, give you a short introduction to the logarithmic function and show you how this equation can be solved with it. In general, an exponential function takes this form, where b is called the base. When dealing with the time dependency of the amount of radioactive material, we have been working with an exponential function where b equals 1/2. In this expression, x is the exponent you have to give to the base b to obtain the value y. This equation isolates y. The inverse function of the exponential function has y as an argument and x as the result. The logarithmic function isolates the x value. It isolates the exponent, which is what we need to finish solving our previous example. In function notation, it is written this way. It does not mean that log base b multiplies y. It means that y is the argument of the logarithmic function with base b. It is important to notice which base is being used because different values for x will be obtained for a logarithmic function with different bases applied to the same argument, y. Routinely, scientific calculators only offer two choices of base, and none of them is 1/2. However, one of them is base 10. For example, evaluating the log base 10 of 10 gives 1, because 1 is the exponent you have to give to 10 to obtain 10. 2 would be the exponent that you would give to 10 to obtain 100. Because 10 to the 0 equals 0, then the log base 10 of 1 is 0. 10 to the power of minus 1 can be written as 1 over 10, which is 0.1. More importantly, the calculator can evaluate the log base 10 of numbers that leads to exponents that are not integers. For example, the log base 10 of 50 gives 1.70 with 3 significant digits, a number that is between 1 and 2. Let us start where we had left off. The goal is to isolate t. Since we can evaluate the log base 10 with a scientific calculator, we will change the base 1/2 into a power of 10. The next step is to recall that the power of a power It involves the product of the exponents. Just like evaluating x squared cubed is equal to x to the power of 6, 6 being the product of 2 and 3. Next, we can evaluate the log base 10 on both sides, since the exponent you have to give to 10 on the left-hand side of the equation must be the same exponent for the right-hand side. The final trick is to notice that the right-hand side is the log of a power of 10, which must be equal to the exponent of that 10. We're almost there. All that is left to do is to isolate t to the left-hand side. Recalling our givens gives this, and the use of the scientific calculator leads to this numerical answer, which is smaller than the half-life. We conclude that the bone is 3,600 years old. So far, our look at nuclear reaction has been mostly about spontaneous decays of nuclei. We made sure that the electric charge and the number of baryons were conserved. What about energy? This will be the topic of the next installment.